Hello everyone, I welcome you all to my YouTube channel. And so basically, from the thumbnail and the description and the title of the video, you you have an idea of what we are going to do on this channel. Usually, I think I'm going to, like, if I continue with the channel, I am going to deviate a little bit from the topics of math, but mostly we'll be talking math. And so today we're going to be discussing the problem number 4 of USAMO. And for those of you who don't know, USAMO is the United States of America Mathematics Olympiad. So let us read the question first. Let H be the orthocenter of acute triangle ABC. Let F be the foot of the altitude from C to AB. And let P be the reflection of H across BC. Okay. Suppose that the circumcircle of triangle AFP intersects line BC at two distinct points X and Y. Prove that C is the midpoint of XY. Okay, so the first thing that should come to my mind, should come to anyone's mind who's trying to solve the problem, is that the point P will lie on the circumcircle of ABC. Basically, these some nuggets, they're usually the starting point to some problem, or you can like backtrack your way through such problems. So yes, I think P lying on ABC is going to be helpful in the problem, and that is one thing that we should keep in mind before starting off. Okay, so I'll be using GeoGebra here. It's a really wonderful geometry like thing for showing geometry. So okay, I have the figure. I have drawn the complete figure beforehand to save time, and you can look at everything that. Okay, this is point A, this is B, this is C. Then I go on drawing the orthocenter and I label it as H, and then I extend CH to meet AB at F, and then I reflect H around BC to get point P, and then after that AFP is the circle which gives me X and Y. Okay, so when I look at the problem, the first thing that, as I have mentioned, the first thing that should come to my mind, even before what the question is asking me, is that AP, BC are all cyclic. And then CP gives me CF. All right. So now I got two concentric circles here. Like I got two circles here. What is a concentric circle? I don't know. So I got two circles here, and I got lots of points lying there. So this makes the question ideal of some, I think, similarity and congruency will show up later. This is a good sign, and I have to work with lengths here. Basically, what I want to show is that in the problem, what I want to show is that Cx is equal to Cy. So what I have to function is in terms of lengths as well. So that tells me that works as a hint. Basically, when I was first solving the problem, I was thinking more in terms of projective geometry. But in the sense that we are working here, it is more of a continuation on similarity itself. So yeah, brute, I think, like simple similarity is enough theory for this question, this particular question. Okay, so this is why, like, I have lots of points on a circle. So that means I have a lot of equal angles because of the arc theorem. So that is the intuition why I'm going to think in terms of similarity. So let us now try to look for the similar triangles in this figure. So basically I want to work around Cx and Cy. So I'll be thinking of triangles that include them. Yeah. So first I okay, so first I think one good idea to proceed in this problem is to get all the low hanging fruits, like the angles that are equal, and then I think it acts as a good starting point to search for the similar angles we're looking for. So one thing that came up to me quite naturally is that XAP is going to be equal to PYB or PYC. So let me call this angle 1. Right. And this is because of the arc XP. This is angle. And let me name BAX as angle. You guessed it too. This is 2. And because of the arc BP on this circle, this is going to be 1 plus 2 as well. And if this is going to be 1 plus 2, what this tells me is that this is going to be 1 plus 2 as well, because HC and whatever this point will be, let's call it E for now, HCE will be similar to PCE. I'm sorry. Yeah, HCE will be congruent to PCE. Okay, so this angle and this angle are going to be equal. So this is 1 plus 2 as well, angle BCH. And because of the external angle theorem, this is angle 2. All right, so we have worked out the angles CPY, the angles in triangle CPY. So now, okay, this is angle 1 plus 2, right? So now, how do I proceed? How do I proceed is that this arc CF, it makes angle 2 in this bigger circle. So it must make an angle 2 here as well, because it's the whole arc thing. That, yeah, which is very preliminary. And so this becomes angle 1, similar to the reasoning we used in the in triangle CPY. So this is angle 1 as well. So now I have got my pair. I have got my pair of similar triangle, and it is, that's CYF. I think I wrote this in a separate text box. Yeah. So CYF is going, okay, this does not work here. I want to show this all in one figure and to make it neat as well. Yeah, I think this works. So angle CYF is similar to angle CPY. This allows me to work intensively with CY, like, okay, because CY length lies in both the triangles. I think that is why I had the intuition to think in terms of these triangles, in these two triangles. So then it carry forwards quite naturally that CY by CF is equal to CP by CY. This is just regular, like, similar triangle stuff, and then CY square is going to be CP into CF. Now what can I do? CY square is equal to CP into CF. And yeah, one more thing that I know from before is that CP is equal to CF. So basically, if I want to, what, CP is equal to CF? No. I have written it all wrong. CP is equal to CH. So, so yeah, CP is equal to CF. So if I want to extend this, CY square is equal to CP into CH is what I want to show now. Now, whenever like I see two products on one side equating two products and the quantities are lengths, one of the first things that I go back to is the power of point in a circle. So I want to bring a power of point quite naturally in this circle. So what is one way to do it? One way to do it is that I use the bigger circle. I think I'll get rid of the angles now because they make the figure quite messy. This is the automating sound. Okay, so CY square is equal to CP by CF. So now, because I have to work with lengths, I was like, if you backtrack a little bit, this thought is like follows quite naturally, really. That now, if we show that CYCX equals cy square or equals cp into cf, we are done with the problem. And it is very easy to see why, right? So now all my attention shifts to showing this. So how do I go about this? Very naturally, I think, like very easy, is that I use power of a point. Now how do I bring a power of point in this problem in itself? That will be to get the point on CH or CF. It's the point, yeah. Computer has given it the name E. So I'll call it like, yeah, I think I gave it a name D earlier, which is why there is in D. I'll just call it D. Yeah. Okay, this is showing D2 because I think I overlapped. But D2 here means D. Alright, so please don't get confused in all this. And then, yeah, I. So now what I need to show basically is that okay, Cy into Cx, Cy into Cx is equal to Cp into Cf is what we need to show. And what this extension gives us quite naturally, what this extension gives us quite naturally is that CD or CD2 here into CF is equal to Cx into Cy. I repeat CF. So now what I want to do is that I want to equate CD with CH or with CP. So now if I do that, I'm done. Right. So this is what I want to do now. I want to show that Cp is equal to Cd or Cp is equal to Cd is equal to Ch. I don't know, like this is the final step, but I wrote it in fifth step. This is not a separate step in itself. All right, so how do I go on doing that? I have a lot of like the only reason why I'm using is because I have a lot of points on a circle. So quite naturally, I exploit that symmetry here as well. And then angle DPA is going to be 90 as well because angle AFD was 90. So if that is 90 and that is 90, that gives me that XY is perpendicular to PD, right? And if that is perpendicular, I leave that to the viewers now. Just like very short reasoning, I think in 2 or 3 lines you will be able to get it yourself. That CP must be equal to CD. And since Cp is equal to Cd, we know that Cp is equal to Ch. So then Cd is equal to Ch. And then Ch, I replace in this statement Cy into Cx is equal to Cp into Ch. I know that. And then I divide this by the lower part of this one, to get Cy by Cx is equal to 1. And thus solving the problem. So okay, this is where I leave you now. And if you like the video, like check out the other videos here. Thank you. I'll be working on more such math problems. Thank you.